Okay, welcome to yet another fun machine design lecture. Yes, this is the fourth lecture I've given this week. This one is more of an example, so if you're having troubles with static failure, understanding static failure, hopefully this clarifies some of it. We kind of went through static failure pretty quickly, so I wanted to go back and give an example in lecture format like this, rather than just relying on the in-class session that we did last week. So, what we're going to do for our example today is, this isn't going to be terribly challenging. The idea is you've got a circular beam, it's mounted to a wall or a plate or something, and this has a torsional load, T, applied to it, and a shear load, F, that is applied to it on this end. We're going to say that this is 6 inches long. We'll say that T is going to be equal to 900 pound-inches. We're going to say that F is equal to 2,000 pounds. We'll say that the circular cross-section shape is a solid circle with a diameter equal to 2 inches. Okay, and then we'll also say that this has a yield strength that is equal to 40 KSI. So, fun times here. We have all the information we need to get going on this. We know all of our geometric properties. We have our loading. We can go ahead and draw a free body diagram. Gonna need Y, X, and then in this, for this configuration, that would mean this is Y and Z. So this goes with that, and this one goes with this. Okay, cool. So in the XY direction, if I were to draw a free body diagram, it would look like this, T, and then this is MXX, because it's an X directional moment. That's torsion, it's a torsional moment. Then we have force F, which means we are also going to have reaction force Y. Because we have these two forces and they're in opposition to each other, we're also going to have to apply a moment to counterbalance this. So I'm going to go ahead and draw moment M like that. Okay, so this is nice. I'm going to go ahead and plot the shear force and moment diagrams for this. So shear force for this configuration is actually going to be negative. So our Vy, because it's in the Y direction, because this is XY, is going to be a constant at negative F along the entire length of the beam. Okay, for our moment diagram, we have two moments that show up here. We have an MXX, and this is an MZZ moment. Torsional moments can be drawn with these two arrows. If they're drawn with the two arrows, they point in the direction of wherever they're being applied. So here, this is an MXX. We could draw every one of our forces just using this diagram. Okay, so the moment starts here, gets increasingly negative, and then at the end of the beam, it reaches a value of F times the length of the beam, which is 6. So 2,000 times 6, which is negative 12,000 pound-inches. Okay. And this is MZZ. And then I can draw our MXX. Our MXX is positive, and it stays constant across the entire beam at T. So these are all three of the loads that we have active. we've identified the loads. Each one of these loads is going to create its own stress. And we can calculate that stress at any position because we know what the loads are at every position. This is our, this is the x-axis, the x-axis, the x-axis. Okay. We know what the loading is at every condition. We can figure out what the stresses are. It's just a simple use of the calculations that we have. So, taking these values, gonna take them and then turn stresses out of them. The critical location here are, first of all, we have the point of application of the force. We have a point of application over here where there's a boundary condition. Point of application of force. We have a maximum moment right here. So just based on this, these two loading conditions are identical here and here, but this one does not have the moment loading, which means that this is going to be our critical location because every one of these graphs has a maximum loading condition. So this right here is our critical location. Okay. Shear force, we can assume that the shear stresses are constant along the entire beam. We're going to go ahead and say their max shear values. We have the moment value, which mxx is a torsional, which if we look at from the torsional, the torsion value has the highest at the edges. Similarly, we look at the bending moment. The bending moment has the highest at the tops and bottoms. So it looks like the top of this circle is going to be where our maximum stresses occur. Okay, so we're going to go ahead and say critical point at x equals L, which is the very end of the beam. And I'm going to go ahead and say top of beam. We could say bottom too, doesn't matter. The stresses are going to be identical. You could actually calculate on both top and bottom. You will get different answers for both the top and bottom because one of them is negative. So here we know Vy is equal to negative F, which is equal to negative 2,000 pounds. We have Mzz is equal to negative 12,000 pound inches, and we know Mxx is equal to, not a negative, but a 900 pound inch torque. Super. So now we've got our critical point. We know what our loading conditions are. These transfer very easily into stresses. The equation for shear stress is tau. Well, if we're trying to figure out the direction of this is a y-directional load that acts on an x-directional face, which means this is a tau xy, or a tau yx, they're the same thing. And the equation for that is equal to Vy over ax times c. If I look it up in my book, the value for c, which I think it's 2, but it may not be 2 now that I think of it. Come on, yep, there it is. 4/3 V over A. Where C is 4/3, and again that's from table 3.2 on page 111. Okay, so tau xy is equal to Vy is negative 2,000. Ay is equal to what? Pi over 4 times 2 squared, because that's this, pi over 4 times diameter squared times 4/3, and that's going to be equal to, let me grab my calculator, negative 848.8 psi. Okay, that's awesome. The equation for this is this is a bending moment, so the equation is sigma x. This bending moment is going to create a stress that comes out of the plane in the x plane is equal to mzz times y over iz. Yes. And this is equal to mzz is negative 12,000. Y is going to be 1 inch because it's a 2-inch beam, divided by the equation for iz. Going to the back of my book. I think it's like, yeah, pi d to the 4th over 64. So pi over 64 times 2 to the 4th. Which I think 2 to the 4th is 16. Nope, never mind. So this becomes 1,000 divided by pi divided by 64 times 2 to the 4th, which is 16. Ends up equaling negative 15,279 psi. Okay, and then lastly, the equation for torsional stress is tau. Now we're looking at the top of the beam here. At the top of the beam, this is the ZY face, which means it is acting in the Z direction on the X facing face, which means this is a tau XZ, and this is going to be equal to T R over J. T is equal to 900 pound-inches, R is equal to 1 inch, and J is equal to pi d to the 4th over 32. Okay, so plugging that in, this is equal to 573 psi. Okay, so 573 psi, negative 15,000 psi, and then negative 848 psi. Okay, we can already see that there's already one order of magnitude difference here between the bending stress and either of these other two stresses, but we're still going to calculate them. We're going to go ahead and consider that all of the stresses are valid. So next step is we need to find our principal stresses. In order to find our principal stresses, we need to plug it into the giant equation, and we need to solve the giant equation for sigma A, sigma B, and sigma C. Okay, we're going to have to solve for all three of them. Oh, I just completely erased that. I have no idea what I put for my sigma y. I think it was 40 ksi. Sy equals. I hope that's what I put down. I can't promise you there. We'll put it into the giant equation. I'm not going to write the giant equation down. I really need to come up with a formula that just automatically solves it. But here, the values that we know for this massive equation. Let me find it real quick. Boop a doop boop, boop boop a doop boop, boop a doop boop, boop boop a doop boop, shooby dop, boopity bop boop, shoo bop bop dop dop. Oh, it's always in a hard place to find a place. Shoo bop, boppity bop bop bop. Yep, bop bop bop. Okay, it's on page 101. And it's equation 315. Okay? And what I get from my equation when I plug everything in is, first of all, I've got sigma x is equal to negative 15,279. I've got tau, sigma y equals 0, sigma z equals 0, tau xy is equal to negative 849 psi. That's a y. Tau yz is equal to 0, and then tau xz is equal to 573 psi. Sweet. So when I plug this in to this equation, grab my calculator real quick, what I get is I get sigma cubed minus this ends up being a negative 15,279 sigma squared. And then plus 104,930 sigma minus 0, because none of the stresses end up coming out nicely. Oh, that's fantastic. YZ. Huh. Okay. So we know right away that sigma A is equal to 0. So that's fun. I'm going to go ahead and solve the quadratic formula. Boop. The 1, that's a 15,279, and that's a 104,930, and sigma, that's an A. Sigma B is equal to negative 68.98 psi, and sigma C is equal to negative 15,210, which seems to me like I might have done that wrong. No, I didn't. Nice. PSI. Okay. So with these three values now, clearly sigma 1 equals 0, sigma 2 equals negative 69 psi, and sigma 3 is equal to negative 15,210 psi. Okay, I can go ahead and say, all right, this is in compression now. This is going to be very strongly in compression at the top of the beam. Had I done it at the bottom of the beam, no. It's actually going to be in tension at the top of the beam. It's going to be in compression at the bottom of the beam. I should have used a negative Y value. But anyways, this is for the bottom of the beam because it's in compression. This could fail in compression. You do it for the top of the beam, it would have been a different value. Now what we do is we apply our failure theories. Okay, I'm going to go ahead and use von Mises stress because I feel like von Mises stress is something that you're going to be working a lot with through SolidWorks. So it's kind of important for you to know von Mises stress. The equation for von Mises stress is, I'm going to erase this work over here now. sigma prime is equal to sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared divided by 2 to 1/2. Okay, so doing this math quickly, again, I'm not showing all of my math here because I'm fantastic. This is 4761 plus 15,141. Oops, sorry, that's wrong. I gotta square that. 229,249,881. That's 229 million. Plus 231 million. And 4,400 divided by 2, and then take the square root of it. So we have 761 24981 plus this is sigma prime is equal to 15,175.6. So that's nice. Sweet. Okay, so this is our von Mises stress now. What we do for our failure criteria here is N is equal to Sy over sigma prime, which Sy is 40 KSI, so this is 40 divided by 15.175, which is equal to 2.636. So we have a safety factor of 2.636 for this component failing statically just using these loading conditions. That's it. All right, I'll see you in class this week. Hopefully if this doesn't help clarify any questions you have for the quiz, please let me know. I can